Okay. Shy of what? Look at me. Look at the old man that's, you know, having to. Okay. Okay, so here we are. Okay, lab number 2, and we are going to talk about, of course, the project and slideshow from the beginning. Okay, so there you go. I turned off the subtitles, so therefore we shouldn't be getting bothered by that anymore. And I'll just push this out of the way. Okay, now, guys, mouse. Okay, now this here, okay, this here is a girder Gerber system. Okay, now just so that you guys don't you know, like, this is just to give you an idea what a girder system, because when we're going to be designing our roof structure, we are going to be using this system. Okay, and basically what this does is that I know that you guys are having just a hard time like taking this all in, but we'll take it one step at a time. Okay, let me just okay, so basically this, of course, is only done at the utmost level of a steel structure. In other words, this can only be done at a roof structure. In other words, if you have floors, columns go through the floors, you cannot do this for a floor if you're going to have, you know, 3-4 stories. It's only at the roof system that you can use the system. Okay. In other words, so here, what happens is that you see, here's a girder right here. Okay, and what you do is you let the girder overhang over the column. In other words, you create a cantilever here, okay? And you create a cantilever there. And if you want, you can create a cantilever here and so on, okay? So and then of course you have a cantilever here. So what happens here is that by creating these overhangs, okay? If I didn't have an overhang here, just so you can appreciate what happened, if I didn't have an overhang here, my bending moment would be only positive, like this. Okay, I would have a big bending moment like this. Fair enough? That would be, for example, if my beam went from here to here. Now, by creating these overhangs, I'm taking part of this positive moment here and I'm redistributing it to the negative part of my beam. So basically what happens is that instead of having a big positive moment here because it's simply supported, I take part of this and I redistribute it into the negative regions. And therefore, by doing this, my MF, instead of being, let's say, I'll give you an example, 600 kilonewton meter, it could drop down to 400 kilonewton meter because I'm bringing 200 of that up into this region here, okay? So this way of redistributing that moment into the negative region of the beam, because the beam itself, okay, this part here and this part here, okay, has the same moment resistance. The only difference is that it all depends on the unbraced length, the LU again, okay? But as far as the MR for the bottom flange is the same MR as the top flange, so therefore the steel has the same resistance whether the moment's at the bottom or at the top because of the symmetry of the beam. And therefore, this smart engineer called Gerber came up with what they call a Gerber system. He thought of saying, instead of having just 2 columns and putting my beam in between and having it, you know, having like simply supported and having a big moment here, let me cantilever here, let me cantilever here. So what I can do, is I can bring some of that moment up here, reduce that moment up there, bring it up here, and therefore I can have a smaller shape or a smaller profile that will be able to perform and carry the loads as if it was simply supported. And this guy, if I'm not mistaken, guys, you can double check, Google it, because don't take this for a word, but I think this guy came up with the system in 1837. I'm not sure. So if somebody wants to Google it and correct me, please do. But I believe that Gerber came up with the system in 1837, okay? So it's been around for a while. Do you agree? I mean, it's almost 150 years. So there you go. Okay, so this is a Gerber system. Okay, and of course here what they're showing you is that these are the open web steel joists, the steel deck and all that. And of course we are going to be applying this to our project. And does anybody have any questions before I go on? Now you see here, this here is the beam that gets suspended. So even for this beam here, okay, even for this beam here, instead of it spanning from there to there, the span would only be from there to there, and therefore even this would end up being a smaller beam. So these drop-in or these link beams end up being smaller than you actually need. So there's a benefit at the end of the day of using this system. Showing vertical.
Sorry, so the one that says suspended set segment, it starts when the cantilever segment ends.
Yes. In other words, it starts
So
where
it
the
doesn't overlap.
No, in other
Okay,
words,
would overlap.
like excuse me, Rena, they come side by side like this. You understand?
Are they welded together?
We will actually design the connection for that.
Okay.
We will do that for the project, okay? And I'll show you how to do that because that becomes a special connection. I will show you that for the project, but it won't be required for the lecture, okay? But I will show you how to design that, okay? So now, okay, so clear all drawings, okay. So basically, so here's a part that's overhanging, there's a part that's overhanging. So you see, Rena, do you see the one that you're asking me? Okay, we're going to be doing our own connection. We won't necessarily be doing, we can do this one, we can do we'll be doing our own, but this is the suspended span, or see, some call it suspended span, some call it drop-in beam, some call it a link beam. Wow. Okay, so, but if I ever talk about the drop-in beam or the link beam or the suspended span, I'm referring only to this beam here that's being supported at the tip of these overhangs or at the tip of these cantilevers, okay? Now, something else I want you to notice here, okay? See these things? These are knee braces, okay? We talked about this a bit when we were going over the open web steel joist, the catalog, okay? We will be doing this, and I will repeat this when we be doing this, because what this does is that, okay, this helps to provide the lateral support to the negative part of the beam, okay? So therefore, this is, we will be doing this, and I want to, okay? So like I said, if this beam here happened to be just going from here to here, from there to there, from there to there, like a simply supported, okay? The moment would end up looking like this. The moment would end up looking like this. The moment would end up looking like this. And by having the overhang, I take part of that moment and I bring it up here. So therefore my MF gets reduced. And since my MF gets reduced, I can reduce the size of the beam that I need to get my MR. So that's what we're doing, okay? Now, so we are going to be doing this. Now, remember, this was our project. I'm going to bring this up so that we can see. Remember, we have, in this direction, we have 3 spans of 9 meters, okay? And in this one, we have 5 spans of 10 meters, okay? And guys, just for your own information, okay, if ever, I don't know if you know, does anybody know what this is called? What's that called?
Bay.
Isn't it a bay?
Exactly, guys. I want you to start learning the term. This, when they refer to a bay, they're talking about the area that is, you know, encased in four columns. Okay, that's a bay. Okay, so that's a bay. Thank you. Who said? Who had the answer? Very good. You know, I'm glad you're. Now, just so that, okay, so now that we're talking about, so therefore, as we talked about before, from here to here, and of course, in every one of these, okay, we are going to have open web steel joists. And last week we determined that the depth of the joist was, I believe, 650, if I'm not mistaken, right? So those are the open web steel joists. So we're going to have them here, and those are going to happen here also, and those are going to happen here also. So all of these are open web steel joists. Fair enough. After that, this is going to be our Gerber system. You see how the thing overhangs here? You see how it overhangs here? See how it overhangs there? See how it overhangs there? This is, so these are going to be the Gerber girders, okay? So this line here is going to be a Gerber girder, and of course, because this width here is the same as that width there, and therefore, whatever we design for this axes, it will be exactly the same design for this axis, because the loads are all the same, and the geometry is all the same. So whatever design I do for this one will be repeated to this one. So we don't have to design this one and this one. Now, if for whatever reason, the columns would not be the same here, they would be offset or whatever, you'd have to, of course, modify that, right? So these are the Gerber girders, and it's the first thing we're going to be designing. Well, I mean, the first thing we actually sized was the open web steel joist, and we said that they were going to be 650 millimeters deep, maximum or minimum, okay? And then the next thing we're going to be designing, of course, are going to be these Gerber girders, okay? Then after that, what we're going to be doing is we're going to be designing the perimeter beams, because the perimeter beams, these are going to be beams, okay? We're going to design the beams on the long side. We're going to design the beams on the short side. After we design the beams, of course, we're going to design the interior columns, okay? But we'll do the interior columns, and of course, the interior columns are here. Sorry. The interior columns are going to be right underneath here. This is where the interior columns are going to be. And of course, then we are also going to be designing the exterior columns, but because these are going to be columns are going to be subjected to wind and axial loads, I will not make this part of the course. I only will design these, and I'll show you how to design these in the lab, okay? Now, what do you think these are in between the columns?
Wind beam?
They are, well, there's somebody, I'm glad somebody said it.
Wind columns?
They're wind columns, okay? So in other words, these are placed here just to minimize the wind load on the principal column. So these are called wind columns, okay? So those are wind columns, very good. And then after that, we're going to be designing these braces. Okay, what do the braces do? Well, all the lateral loads that are imposed on our structure because of wind or earthquake, they get transferred to these things, and these things go and they transfer the loads down to the foundation, and hopefully everything's going to be stable and won't collapse on you. And then the last thing we're going to be designing, or one other element we're going to be designing, are these things here. These things are called girts. Okay, so these are members that are put in the walls. So when the architect, when he comes and puts his exterior wall panel here, they'll be able to attach it to these members here. So it will get attached here, it will get attached there, it will get attached there. And of course, they'll worry about how to attach it to at the foundation level. So these are girts, okay? And we will also design the girts. So these are the things that we're going to be designing. And basically, we're going to be designing everything. And on top of that, we're going to be designing the connection here. We're going to be designing the connection here. We'll be designing a few connections, okay? And that we're going to learn in the course. Okay, so this is basically the elements that we're going to be designing. And of course, the first one we're going to start with are the Gerber girders, okay? So now, this is, guys, I can do two things. You can either, we're going to start modeling the Gerber girder as if we want to input this into ADA, okay? So I don't know if you guys want to copy this, or if you want me to send you the lab, I can send you the lab and you guys can have all this information. It's up to you. Tell me what's easiest for you.
Can you send us the lab, please?
Yeah, can you send us the lab, please?
Yeah, I can send you the lab at the end of the lab. I'll send you the PowerPoint. How's that? Sounds good? Okay.
Yes.
I would rather you guys follow so you know what you're doing, and then after I send you the lab, you guys can start doing this on ADA. Okay. So let's do it that way. Okay. So this way, I'd rather you guys just look at the screen and then be able to follow me. So guys, here is the, okay. So this was, if I go back, okay. So I'm doing an elevation along here. Everybody sees what I'm doing? So this is the elevation. Now, wherever there's a column, I don't necessarily model a column. I can with ADA, but I never do that unless I'm doing also my lateral loads, okay? So what I do in ADA, okay, wherever I have a column, it's a support, okay? So therefore, this is a support, 10 meters. This is a support, this is a support, this is a support, this is a support. Now, the thing that's important is that if you're going to be putting supports as opposed to putting actual columns in here and then worrying about how it's going to be fixed here and all that, you're going to be pinning it only at one place. So in other words, you have a pin support here. The rest are all rollers. Now, if you happen to put pin, trust me, it doesn't change much in terms of the analysis. It won't have a great effect. But if you put fix, that is totally wrong, and your analysis is going to be totally wrong. But I do recommend that the more conservative thing to do is to put a pin on one for one reaction, one column here. So this would be the exterior column here. This is the interior column here. This is the interior column there. That's the interior column. That's the interior column. That's the interior column. And that's the exterior column. But put a roller, because you let the thing kind of, you know, come back and forth, because there's nothing that really restricts it from moving under the loads. Okay. Now, so therefore, we know that we have a 10-meter span, 10-meter span, 10-meter span, 10-meter span, 10-meter span. In other words, 5 spans, which gives us our total of 50 meters here. Now, the overhang, this is the overhang. So in other words, we have this overhang will make it 2.5 meters. And then, so in other words, whenever I refer to the left cantilever girder, I'm always referring to this one here, the left cantilever girder. Okay, now I won't refer to this one because when I'm going to show you the load cases, it's going to, whatever happens here, if you do the mirror image, is going to happen to this side. So I will always refer to this as the left cantilever girder. This is either, I will mix and match my words. I'll call this the suspended girder. I will call this the suspended segment. I'll call this the drop-in beam. I'll call this the link beam. I just want you to be familiar that if you read other textbooks, some people call this a drop-in beam, some people call this a link beam, and so on and so on. Okay, so here what we're going to do is that we're going to make the cantilever here, the overhang or the cantilever here 2.5 meters. On this side, we're only going to make it 2.2 meters, and it's going to be symmetric on this side. And of course, in order to create this realistically, this member is going to be pin connected. I don't know if you remember this, but in structural analysis, I purposely introduced the pins in the analysis of beams so that you realize that in a Gerber girder, you do have a pin, a smooth pin here, a smooth pin there, a smooth pin there, and a smooth pin there. And of course, with ADA, to create this is very, very simple. Okay, so this is going to be, of course, the dimensions. Now, in ADA, what you need to do, you need to put a support here, a support there, a support there, a support there, a support there, a support there. You need to put a member from here to here. You don't put a member from there to there. You put a member from here to here, and then you put a member from there to there, and then you put a member from there to there, and then you put a member from there to there, if you remember how to do ADA. So in other words, even though this is a continuous member, for ADA, you need to create 2 members so that the member can interact with the reaction area. The member can interact with the reaction area. I don't know if you remember that, but that's how you do it. I've seen, so anybody that's going to, in ADA, going to put in all these nodes and supports and all of a sudden take the member, go from there to there as one member, that is wrong. You will not get any interaction here. You will not get any interaction here. Okay. So the way that you do it is that this is one member. This is one member. This is 2 members. This is 3 members, and so on. Okay. So that's how we're going to be modeling the Gerber girder and ADA. And what I do suggest is that for a preliminary size, we're going to be using a W, like in other words, you're going to be assigning these, because in ADA you have to assign a shape to your analysis. We're going to assign a W610 by 125, okay? And the reason why I do that is I think that I know by experience that this would be slightly oversized for this geometry, okay? I would rather put something slightly, if I want to be ultra conservative, I would put a W1 whatever, okay? That's just to compensate for the dead load that eventually when I actually size my members, I will always overestimate the self-weight of the beam. So I do this to overestimate the self-weight of the beam. I put something slightly bigger now for my analysis. So this way, when I finally actually design my members, hopefully they will be smaller than this. And therefore, when I redo my analysis, it won't affect my results. So that's going to be the preliminary size. And as far as the material goes, we're going to choose the American material. Okay, what I was telling you before, the A. Anyways, you'll see it somewhere else. I wrote it somewhere else. I think it's the A992, the ASCM A992 steel. Okay, that's going to be the size of the material that you're going to be assigning. We'll assign the American one. But as far as the material goes, it will not have an effect on your results because you're only looking for forces. Where the material has an effect on the results of ADA is if you're letting ADA calculate the stresses. Okay, that's where the material will have a different stress value depending on the material that you choose. But okay, so the material is going to be the A992, the ASM A992. Okay, But like I said, if you happen to pick the wrong material, but you have to pick a material, pick one of the steels, but pick the ASTM A992, you might as well pick the same thing. So if ever you want to do a stress verification, at least you've got the right materials. But we don't do stresses, okay? So that's as far as the dimensions go. Now, this is, of course, what you would input into ADA, okay? So in other words, I have member 1, member 2, member 3, member 4, member 5. So when you're gonna go and model this on ADA, you're gonna go to structures. I'll even open up ADA, so in case you guys don't remember, you're gonna have member 1, you're gonna first place your, well, what I call your nodes, right? These are called nodes. So you're gonna have node 1, node 2, node 3, node 4, node 5, node 6, node 7, node 8, 9, and 10. Of course, the very first one starts at 0. Then where's the first column at 10 meters? Where's the second one at 12.5 meters? Because if you remember, the overhang was 2.5 meters. So in other words, here I have from here to here, I have 10 meters. Then I got 2.5 meters. So therefore, this is at 12.5. And then from here to here, I have 2.2 meters. And this was 20. So what's 20 minus 2.2? 17.8. So the next node would be at 17.8. Then the next node would be at 20. And then after that, I have another one at 30, because this is a 10-meter span, and so on. So these are all the distances for your nodes, okay? And so that's your nodes. And of course, once you place your nodes, 1 and 2 become supports. This node becomes a support, that node becomes a support, that node becomes support, and so on. So 1 and 2 are supports. These are normal nodes. In other words, they're not supports. Then 5 and 6 become supports. And then these become normal. And then 9 and 10 become supports. So these are all the types. So therefore, now you got your nodes, you got where they're placed, and you're telling the program what are supports and what are just normal nodes. Anybody have any questions so far? And I'll be sending you this, so you'll be able to get all this information. And I want you guys to all do it correctly. And I'm not here to retest your ADA skills. I just want you to try it one more time so that you can get a better appreciation of what you did or why you were learning ADA. And like I said, we're going to get a better appreciation doing this Gerber analysis, and we'll do a few other things with ADA, but doing this Gerber analysis is going to give you a better appreciation of why we learn ADA, okay? So that's going to be for the nodes, okay?
Sorry, sir.
Yes.
Can you just repeat, what's the difference? Why do you put some like support and normal?
Oh, because if I go back here, okay, let me go back. This is a support, that's a support, that's normal, that's normal. That's a support, that's a support.
The pins, okay, yeah.
The pin connection becomes a normal node. In other words, we're going to change the condition at the end of the member, but it's going to stay a normal node.
Yeah, okay.
Okay, is that clear, Adriano?
Yeah, it's perfect. I completely forgot about the pins for a second. It makes sense now.
Okay, so it makes sense, good. Okay, now, and of course, these are the members. So you're going to have member 1, I'm sorry, these are the supports, okay? So at the supports, if you guys, I'm not expecting you to remember this, but if you do remember, how do I create a pin on ADA? Well, I restrict RX, I restrict RY, okay? So I fix RX, I fix RY, but it's free to rotate about the Z axis, therefore I free MZ. These don't matter because we're not doing a 3-dimensional analysis. So all of these become redundant, okay? Because it's a 3-dimensional program, these become redundant for us. So therefore, this becomes a pin support, and because I free, all the rest become, of course, rollers. So but RY are all fixed. In other words, I'm only restricting the displacement in the Y direction, and therefore everything else becomes, okay, so, and of course, you always free the rotation. So this is for the rotation, and this is for the displacement in the X direction, and this for the displacement in the Y direction. So this is how you're going to model the supports. And then after that, you have your members, okay? So like I said, the preliminary size that you're going to be assigning is a W610 by 2025, and here's the material, ASTM 9A2025. So that's going to be, when you go, after you add the members, you're going to have to give it some properties, and this is the property. You're going to put them all the same at the beginning, and then we'll modify them as we design them. So now, here are the members. So member number 1 is going to go from node 1 to node 2, okay? And of course, from node 2, the member is fixed. In other words, that's how I create continuity for member number 2. Okay. Now the suspended one, what I'm going to do is I'm going to make it pin on both ends. I don't have to pin it there and pin it there. I only have to pin it on one member. And I know that whoever takes this with the other teacher, I always see the students pin there and pin there. Don't do that. That's redundant, okay? As a matter of fact, some structural analysis program cannot get rid of that redundancy, and if you do that, the program is going to crash on you. This program is sophisticated, and therefore it can overcome that redundancy. So when you want to pin something, I either pin it on this member or I pin it on that member, but I do not pin it on both members, guys, okay? I'll tell you that right now. So therefore, this here becomes the suspended section here, and therefore it's pinned there and pinned there. That means that whatever moment gets created here gets released, and therefore when you do your moment diagram, when you go right through this point, your moment should be 0, okay? Now this I don't care, because we're not in 2 dimensions, and this I don't care. So the only thing I care about is this here, okay? If you guys don't remember where to do this, I'll show you. I'll open up ADA and I'll show you where to do this on ADA. So in other words, 1 would be fix, pin on both sides for the suspended one, fix, pin for the other suspended section on the other side, and then it becomes everything fixed, okay? So at the columns, you don't have to worry if it's fixed, because I know my condition here for my support is a pin, so I don't have to worry about the end condition. That's at the support, so that's why I don't care what happens at here. Okay, so that's for the members. So far we've got the geometry, we've placed our nodes, we modified our supports to represent what they're supposed to be. Then we've added our members, and then we've changed the end condition to the members. And if you do it correctly, and I'll show you where to do this in ADA, if you do this correctly, this is what you're going to end up seeing, okay? You're going to end up seeing, sorry, this thing keeps popping up. Okay, so here's the first member, and then of course it's fixed across here to the second member. This is the third member here, and it's pinned, and I'll show you how to put this on your visual graphics, how you can see these end conditions to make sure that you've done it correctly. And that's what ADA does. If I've created a pin, I should have a little circle there and a little circle there, a little circle there, and a little circle there. And if you guys don't remember how to do that, I'll show you how to do that, not a problem. So this is what you're going to end up seeing in ADA, okay? So in other words, you're going to have a pin, roller, 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 and then this member here is fixed, and fixed, so therefore that fixity is what makes it continuous, but I still have to create 2 members there. I pin the suspended one, so I don't have to pin there and pin there. I don't have a circle there and a circle there, and so on. Okay, so this is going to be the, so I have, of course, if I have 10 nodes, I end up getting 9 members. It's always n-1. And now let's talk about the loads, okay? Now, what happens is here, okay, you'll notice that this is my roof, okay? And what's going to happen is this, okay? Here's my girder, okay? What's the girder actually supporting?
The joists.
The joist, okay? So therefore, all the loads on the joist are going to come and rest here. So what kind of a force am I going to create on the girder?
A normal force.
A concentrated force. Normal, okay, perpendicular to it. I like that word normal, perpendicular, but concentrated, okay? So therefore, every joist, like for example, every joist here is going to, so in other words, this is my joist here like this. Okay, I have a load here. So therefore, the reaction here of the joist is actually the force I'm imposing on my girder Gerber. Okay, so therefore, at every point here, I'm going to be putting a concentrated load onto the girder. Everybody sees that? And of course, how do I calculate that concentrated load? Very simple. I take my factored load. Well, I won't even factor. With AD, I don't factor because I'm going to be using load factors and all that. I take my pressure, whatever it is in kPa, okay, and I look at the tributary area that gets transferred at this point here. So therefore, here I have half of 9, so I have 4.5, Now here it happens to be the same, 4.5. So that's the dimension of all the load here. And then in this direction, of course, is the spacing of my joist. This is 2 meters. So therefore, the tributary area of all that load coming here is going to be equivalent to 9 meters by 2 meters. And that's the tributary area that's contributing to that concentrated load at every place where the joist is supported by the girder. I just want you to see that and understand that. So now, last viewed. Okay, so here, what we say, we have a dead load, we calculated a dead load to be 1 kPa last week. Okay, that's what we said. Is that the value we had said? Is everybody in agreement with that? Okay, good.
Yeah.
So that's our dead load. Okay, now, of course, the dead load times the tributary area from the, whatever tributary area that is resting on the joist, and I just showed you, gives me this concentrated load. And therefore, I end up getting 18K. Now, with ADA, you never factor your loads. You just put in the specified load, okay, as it is. And then when it comes to your load combinations, that's where you're going to come up with all the other, the factor loads. So right now, what's going to happen is that from here to here, I'm going to put 18 kilonewtons, 18 kilonewtons, 18 kilonewtons, 18 kilonewtons, and so on. And here I only put 9. Why do I put 9? Well, because this one has half the tributary area of that one. It's even smaller than 9, but I put 9. It's even smaller, but I put 9 here, okay? I just wanted to show you that in theory, this one should be less than all of these because the area here is only half of what this one is carrying, okay? Everybody agrees? So therefore, I'm going to have okay? Now guys, now, when it comes to the snow load, well, this is where it becomes interesting, okay? When it comes to the snow load, hold on a second. I just don't want to lose track of time. When it comes to the snow load, well, this is where it becomes interesting, okay? The National Building Code of Canada, says that flat roofs shall be designed for the specified uniform snow load indicated, which shall be calculated using CA equal to 1, and that's what we did. We used a CA equal to 1, distributed on any portion of the loaded area and half of the load on the remaining loaded areas in such a way to produce the most critical effects on the structure. So what they're saying is that you have to take into account that you can't just put 100% right across the roof. You have to kind of select. At one place, I'm going to put the full load, and somewhere else, I have to put half the load and see if it's going to be more critical, how it's going to affect my member. Okay, and this is where it becomes interesting. And this is where we get into the different load cases and not load combinations. Okay, these are load cases. So this is what the code wants us to do, and I'll show you how to do this. So don't worry about that. Now, paragraph describes the full and partial loading. Okay, full load is distributed on one portion of the area and half this loading on the remaining area. The location and size of such partial loads being chosen to give the most critical effect to the members and the joints themselves. Okay, so this is what the code wants you to do. Now, how do you apply this? You'll see this in the next slide, okay? So this is load case number 1, okay? What I'm gonna do is I'm gonna say, well, for some reason, 100% of the load is just gonna be in the first span, okay? And then the rest of the roof is just gonna be using only going to be subject to 50%. In other words, is it possible that all of a sudden the wind blows and all of a sudden it builds up the snow? And I've seen this on roofs, okay? I've seen that it blows and all of a sudden it creates a big, a big pile of snow here for some reason, and then here it stays relatively little. So this is one of the load cases that you're going to have to consider and analyze and see what happens here. And of course, what this does, okay, by putting 100% here and 50% there, well, what this does is that it gives you the biggest positive moment that you can get in this span. So you're going to get the biggest MF here, okay? Biggest positive MF. That's what this load does, okay? And at the same time, it gives you the highest load that you can have on this column, okay? But if you have to design the column. So what this does is that causes the maximum positive moment in the left span with a single cantilever and a maximum reaction at the end. Okay, so this is what this load case will do. It'll give you the maximum positive moment here because the overhang doesn't have a lot of, as you can appreciate. So that's load case number 1. Then load case number 2. Okay, Load case number 2 is this. You put only half here, and then you put 100% all the way across to the rest of your roof. So therefore, it causes the maximum negative moment in the left span. So this one's, so the first one gave you the maximum positive moment here. So in other words, what this means, and I'll try to draw it for you so that you guys can see it. Okay. So in other words, the case before gave me the maximum positive moment. This is case number 1, the maximum positive moment here like this. Okay. And then case number 2. And you'll see this when you run the analysis. Case number 2 is going to give you the maximum negative moment that you're going to get up here. So you'll be able to get this value here and this value here to make sure you design it accordingly. So that's what this is going to do. So that's load case number 2. Now, load case number 3. Okay. And of course, this one gives you the maximum moment in the span and the maximum reaction at the second interior column. In other words, this gives you the maximum CF value in this column here. Okay. And we'll see that when we run the analysis. When we design the columns, we'll look at these values, okay? Now, number 3, you put 100% there, 100% on the first span and on the second span, and then you put 50% on the rest. What this is gonna create, it's gonna create the maximum negative moment in the center span, okay? So it's gonna give you the maximum negative moment here, okay? For that, and the maximum positive moment for the suspended. So this one's going to give you the maximum positive moment to design this beam here. It's going to give you the maximum negative moment to design this beam here. Okay. And of course, the maximum column reaction of the interior column. That's going to give you the biggest CF value that you have here. So that's what's going to be happening. So that's going to be from load case number 3. And then load case number 4, you put 50% there and 100% there. And what this is going to create, of course, is going to create the maximum positive moment here. Okay, so it causes the maximum positive moment in the center span with the double cantilever. Okay, so these are the 4 load cases you're going to, you're going to have your dead load. Okay, and so this is which, and then after that, you're going to have 4 different snow loads. Okay, that you're going to have to snow load cases. So now, so this, so remember, okay, so remember. Load case number 1, we're putting 100% here, 50% across here. That was case number 1. So what's going to happen is that, okay, what we're going to do is we're going to be putting 45 kilonewtons per meter here. Of course, here there's only half the tributary width, so that goes down. And all the rest, we're only going to be putting 50%, and therefore we'll only be putting 22.5 kilonewtons on all the rest of the members. And then, of course, here it's even less because it's got half the tributary width. So this is going to be the loads that you're going to be putting, or that you're going to be placing on your members, okay? For snow case number 1. Then snow case number 2, if you remember, it's 50% here and 100% all the way across here. That was case number 2. So what we're going to do is the same thing. Okay, so for 100%, we have, in other words, 2.5 times 2 times 9 gives me 45 kPa, kilonewtons, sorry, kilonewtons. That's for 100%. If I want to put 50% as the code required me, I only take half that value, 22.5. So here I put 45 right across there. On the first span, I put 22.5, and the only reason why I put 11.5 there and half there, because this one only has half the tributary width all the time. Okay, so this is going to be, this is snow case number 2. Okay, then of course number 3 is where you put 100% here, 50% there, and that's what we're going to be doing. Last viewed. We're going to go, and of course, the values don't change. It's just a question of where do I put 45, where do I put 22, and where do I put half the values. So 45 from there to there, 22 from there to there, and then here, of course, I put half of the 45. Even though it's 100%, I only have half, and here half is a quarter. So therefore, here I end up with 22, and here I end up with. Now here, as far as the beam analysis goes, it doesn't make a difference, but when you design the column, it can have a bearing, okay? And then of course, last but not least is where we do the opposite, okay? If you remember, last but not least, where you put 100% there, 50% on the first 2 span, 100% on the rest of the spans. So therefore, we're gonna do that, okay? And of course, these values don't change. It's always the same thing. So I'm gonna put 100% right across here and 50% right across here. And of course, here, half of what's here and then half of what's there. So those are the 4 load cases that we're going to have to do in ADA. And then of course, as far as the load cases go, okay, guys, ADA has dead for self-weight. Don't change that. Okay, do not change that. Leave dead for self-weight. Don't change that. Leave, like, leave that load case what the program decides. Don't modify that. I don't know, some people modify that. I don't know why. Just simplify your life.
Sir,
Yes.
when we were with the infrastructure analysis with Jade, Jade told us to modify it all the time.
Why?
I don't know. She just said that every time that load modified to self-weight.
Why? Why do you need to modify it? The program has that as a load case. Why do you want to modify it?
Yeah, I don't know what she just meant us to do every time.
Like I'm asking you, why do you, like, in other words, did you ever ask her, why do we need to modify it?
Not
It's,
really.
it's only additional work because you're gonna have to modify that, and then you're gonna have to call another load called dead load. Is that it?
Exactly. Essentially,
Okay,
that's what we're
so
doing.
why do you want to give yourself that extra work when it's
Yeah,
already
it's-
called dead load, and you know that it's the self-weight of the program?
Yeah, no, it's pointless.
You follow what I'm saying?
Yes, sir.
Now, how do you distinguish dead load? Well, in reality, in real life, the dead load that we calculate that's being carried by the member, I call that superimposed dead load. That is what it is. It's a superimposed load on the member. You understand? And what I call that in AD, I call that SID. So instead of changing dead to self-weight, just create another one called SID for the superimposed dead load. And that's your 1 kPa or whatever it is. You understand? And that's what it really is. It's a superimposed dead load. Do you agree?
Yes.
Okay, so now all I'm saying is that, so these are the names, like, in other words, I don't change this. This is created by the program, so I don't want to modify that and spend my time calling that self-weight. I will have one, for the dead loads themselves, I call that superimposed dead loads, and I know that these are the ones that I have actually calculated, okay? Because as a matter of fact, in the superimposed dead loads, I have not included the self-weight of the member. The program will do that for me. You understand? And that's why I like to separate them. Now, after that, I'm going to call this snow P1, okay? And that's going to, actually, these are the names I will be giving to the load cases. Snow P1, and that would be the snow load pattern 1, the one that we saw. Then I'm going to have snow P2, snow P3, snow P4. So this is snow load number 1, snow load number 2, snow load number 3, snow load number 4. Okay, and this is pattern number 1. And the reason why I put 1 P here, so I know that it's pattern 1, pattern 2, pattern 3, pattern 4. I know this is 100% on the first span, all of it, 50%, and okay, so that's why I call these, okay? So that's going to be the load cases that I'm going to create in ADA. In other words, in ADA, I will be naming these load cases from here. These are going to be the names I'm going to give to ADA for the load cases, and this is what I'm actually going to put down the values, okay? And this, of course, gets calculated by the software, so I don't care. So that's what I'm going to call them. Now, so for the dead load, this is what it's going to look like. Remember? Okay, so in other words, the dead load I'm going to have here. So this is the SDI in ADA. So I'm going to start assigning minus 0.9 right here at the first. Then at 2 meters apart, I'm going to put 1, 2 meters, at 4 meters, 6 meters, 8 meters, 10 meters. Okay. Then on the next member, it's going to be at 2 meters. Now here you have to be careful because you got to remember, you got to be careful when you assign this load because from this is the member, right, from there to there, and this is 2.5 meters, okay? So therefore, and these are spaced at 2 meters apart, so therefore there's 5 meters here, and then this one is at 2 meters, so therefore the load on this member is only 1.5 meters away from where it starts, okay? That's where you apply that one. And then if you do it correctly, they should be all evenly spaced all the way across, and that's going to be your superimposed dead load, okay, that you see on ADA. Then as far as the snow load goes, well, this is what pattern 1 is going to look like. Now, like, I don't know if you guys know how to do this in ADA, but once you put these values in, you can copy them and then put them in here. So this way you'll have all the same spacing. So I don't care how you do it. And then after that, these are the values for P1 that you're going to have in ADA, just as we saw, okay? And then of course, you're going to have P2 is going to be this, and then P3 is going to be that, and P4 is going to be that. So those are going to be the 5 load cases that you're going to actually input, okay, with all these values. And then now that you've got your load cases in, now you go to the next step and you worry about your load combinations, okay? So what you're going to do then, once you finish this, the load combination is going to be, okay? So the load combination is very simple, okay? You're going to have P1 dash ULS, okay? P1 means for snow pattern number 1, and you call it ULS because it's going to be ultimate limit states. In other words, this is going to be for strength, or you can call it P1 strength. You can call it whatever you want, but I like to call it P1 ULS. In other words, I know that this is ultimate limit states. This will be for my strength, whatever you want to call it. Now, for this load combination, I will take 1.25 times the self-weight of the member plus, and then I'm going to have another one, you know, like when you and then they're going to be add another line. I'm going to have 1.25 times the superimposed dead load, and then I'm just going to multiply 1.5 times my snow load. So in other words, this is going to be load combination 3 that you have. This is load combination 3 for snow case number 1, okay, if you want to look at it from, okay. So this is going to be for P1. And then, of course, for P2, you do the same thing. The only difference is that this stays the same for P2. You still have to create, you know, another combination called P2 ultimate limit state. So, you know, this is for strength. And you're going to multiply, and then you're going to replace, you're going to put here snow P2. You're going to call it, and then you're going to multiply by 1.5. And then you're going to do it for P3. And then you're going to do it for P4. Okay, so these are the load combinations. So 1.25 times your dead load, 1.25 times your superimposed dead load, and then 1.5 snow 1, snow 2, snow 3, snow 4. So this is how you get your design loads with ADA. You put in all these specified loads, and in the combination, this is where you put the load factors. In other words, based on the limit states design load factors. And we know that for snow, it's 1.5. And when you combine the dead load with a variable load, we know that's 1.25. And that's why we have 1.25 here and so on. Is that clear to everybody?
Sure.
Okay. Now, once you've done your load combinations, what I love about ADA, and if you guys don't know how to do this, I'll show you how to do this, okay? Okay, then you have what we call serviceability. In other words, you want to check your deflection. So once you've sized everything and you want to see if the deflections are within L over 240 or L over 360, then you're going to have just your snow load, which is serviceability limit states. And there, since it's only going to be snow, you're going to take your snow load number 1 and you're going to multiply 1, because for serviceability, we do not factor the loads. So therefore, we're going to check serviceability under load number 1. We're going to check serviceability under load number 2, and we're going to check serviceability under load number 3, and we're going to check service. So we're going to have 8 load combinations, okay? 4 for strength, 4 for service, and we'll check each one to see what the results are. And then ultimately, if we want to see all these results combined into one diagram, what are we going to do? I don't know if you guys remember last year we did the shear envelopes. Well, in ADA, you can create moment envelopes, you can create shear envelopes, you can create deflections, whatever, okay? So for the envelopes, and I'll show you how to do this if you guys don't know how to do this, okay? You're gonna have one for ultimate limit state, and you can call this strength, where you're gonna put P1, P2, P3, P4, and what the program is gonna do is gonna look all of the results of P1, all of the results of P2, all of the results of P3, all of the results of P4, and it's going to combine them all into the envelopes, whether you're looking at shear, moment, and so on, okay? So that's what, and then after that, you're going to do the same thing for serviceability so that you can look at all the deflections, okay? I personally, for serviceability, I like to look at each one individually to see how each one is creating, because under the envelope, it doesn't give you but at least you'll get an overall view of what it is. But the serviceability is not important. But as far as strength goes, this is good. Like I like this. But this here is not necessary. But if you want, you can create that also. So these are all your load combination. And then once you've done all of this correctly, guess what you can do? What's the next step?
Analysis.
Exactly. You hit FX, analyze, and you're done. You see? And that's what's nice about ADA. Then everything gets done. All the moments get calculated, all the shears get calculated, all the displacements get calculated, and so on and so on, you know? So Then once you run your analysis, okay, that's it. Okay. So what I'm going to do is I'm going to send you this. I'm going to send you this. What time is it now? Do you guys have? Oh, okay. Exactly. I did this purposely so that you guys can get started on it. Do you guys have access to the ADA? Do you have access to -2H27 on your computer through VM Horizon?
Yes, we do.
Yeah, we do so.
Okay,
Sometimes it's a bit sketchy, the connection. but-
Okay, well, exactly. So this is why I'm not forcing you guys to do it right now. Okay. What I'm going to do is I'm going to stop sharing. First of all, I'm going to put this on pause. This, okay. So here you go. We're being recorded again. So here. So first thing you should do is, of course, you click here, open up a new file. I can't do that right now because I've got an existing file. So you click a new file. Okay. You click a new file. Once you open up the file, the first thing you should worry about is you go to project configuration here, and you go to preferences, and these have all check marks in here. Okay, these are dialog boxes that are going to pop up as you assign one member. There's going to pop up a dialog box. Since you don't want those things to jump up in your face, you simply remove all the check marks in here. This way you can control the pop-ups of the dialog boxes. Then the other thing is, I think by default, ADA starts with metric shapes and metric units. So make sure you press on metric here. Make sure your radio button here is on shapes. And that's the other thing you should adjust. And then the last thing you should worry about, I think by default, it's all set at 10 here. So don't change this. Don't go to 20, don't go to 40, don't go to 100, even though the program can do it. 10 segments for this length of member is ample. And then I'll show you next week that it doesn't make sense to go over 10. You understand? Like, in other words, if ever you want to start printing out your tables, you're going to have, if you ask 100, if you print out a table, you're going to have 100 rows just for one member. You're going to have 100 rows for another member. So here I have nine members times 100. I'm going to have 900 rows of information that, in theory, I will never use. Okay, so leave it at 10. Okay. Sometimes what I do, depending on what analysis, sometimes I even redo this to 5. I redo this to 2. It depends what I need to do. So just let you know. And very rarely, unless I need to go very specifically along the beam, I have to get a value very, very precisely along the beam, I will maybe run one analysis at 30, get that value, then I'll go back to 10. So leave that the way it is. Once you fix your preferences, you're okay. Then the first thing you do is up here under structures. Okay, I'm pointing at the structures. You click on structures, and this is where you start inputting. So the first thing you do is you go to nodes, and of course you click on this plus sign here, and it keeps adding. You know, you start plus, 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 plus. In other words, you do it at least 10 times. I'm gonna remove this one here. I don't need it. So I'm going to delete that one. So you put plus, 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 plus. In other words, you do it up to 10. So open up 10 rows. This is a spreadsheet. This, believe it or not, this is an Excel spreadsheet. Okay. And then after that, you start putting your dimensions here. The first one starts at 0, and then you go to 10, 12.5. So if you followed, if you have all that, I showed you that on the PowerPoint. So the next member is at 12, the next node is at 12.5, the next one is at 17.8, then it's at 20 because it's a 2.2 meter overhang here. Then there's a 10 meter span between the two columns, 30, 32, 37, 40. So this is the spacing of your nodes. And this here, you click on here, and this is where you can change from normal to support, normal to support. So you can just click on there and you can change. The only one that's normal is node number 3. Node number 4, node number 7, and node number 8. Those are all normal. So that's what you do there. That's what you're going to be doing there. Okay. Then once you've done that, you come back out, you'll see all your supports here. And then after that, what you need to do is you need to go and adjust. First thing I like to do is always model my supports so that I don't accidentally leave them as fixed, fixed, fixed. So once I've done that, I've done my notes. Now I go to my supports, and this is where I change my support. Support number 1, fix, fix, free. Then support number 2, in other words, these I don't worry about. Like I said, this is only for three-dimensional analysis. I don't worry about these RZ, and all that. Then here I put free, fix, free. Okay, so in other words, I free up all here, and this is all free under MZ. In other words, the rotation about the axis that is perpendicular to the screen. That's what MZ is. And therefore, but the Y is always fixed. In other words, you do not allow any displacement in the vertical direction, whether it's upwards or downwards. So that's how you model the supports. It's all here. And of course, once you've assigned the supports on your nodes, when you pop this up, when you pop this up the first time, this is all going to be fixed. Everything is going to be fixed here. And that's what it is by default. It fixes everything. And then you're going to have to free whatever is not fixed. So what does a roller mean? It means it's free to go back and forth in the X direction. And therefore, I will make that free. What does a pin mean? It's not free to go up and side to side, not free to, but it's free to rotate. Therefore, it's free to rotate. That's what MZ is, okay? That's what all the MZ is, okay? Then once I've done that, I come here and I click here on the plus sign, okay? I click on, and then I can't do it now because I don't have to add any members. I click on the plus sign here. Well, first of all, I make sure I'm on members here. Okay, make sure that you're on this vertical bar, you're on members. You click on the plus sign, you're going to get this, and you're going to be able to go from one node to the next node. And guys, be careful. I don't know if this was explained to you, but when it comes to analysis, if you start here and you go there, when you see the results in ADA, it will start the results on this side and go to this side. And then be consistent. So this way, when you look at the results, you realize where it starts on the member and where it ends in the member. So if I go from, this is I, this is J, this is I, this is J, this is I, this, so always add, like be consistent. I don't care, but don't go like one member there to there, and then one member there to there, and then you don't remember which one is I, which one is J. Be very consistent. Add, always go from left to right, left to right, left to right, left to right, left to right. This way you know that you're moving from the beginning of the member to the end, beginning of the member, and this way when you look at the results on the table, you know at which side is there, that's and what's happening at the other end. So you add your members. Once your members are added, then you simply click, like what you can do is you can pick them all, okay? You can pick them all at the same time, okay? And you right click on them, since they're all gonna be the same, you just go to properties, okay? And of course you go to properties, and this is where, you know, you click here and you go under steel and you go under W shapes, okay? You're gonna go under W shapes here. Oh. And you're gonna go under wide flange, and you're gonna go down and you're gonna pick a W610. So like I said, to compensate for the dead load, I pick something I know that would be a little heavier than I need, just so I make sure I account for the self weight of the beam. I'll be on the conservative side, so I go for a W, and therefore that would be the member, okay? And then I press OK, and all those members are gonna be assigned that. I'm not gonna do it because I've already assigned that. And then after that, once I've done that, I come to material, I go to steel. Of course, I'm using the American steel, unfortunately, and then I go to A922. So this is the steel that we use. This is the American steel that they use to roll the white flanges. So I would pick that one, double click on it. Ooh, sorry. And then of course here, if I want the program, I make sure I put dead here so that the program will calculate the self weight of the member, and I leave that as dead, and that's it. And I press OK. And guys, what I do recommend, okay, is when you are doing this, okay, one of the things, oh yeah, the last thing I want to talk about, so that means that all your members have been assigned their properties, their materials, you're almost ready to move on to your load cases. So now, once you've done that, what you're going to do is this, okay, like what I strongly recommend is that whenever you're starting to model, okay, one of the things I recommend you do is that open up your, see here, your your view options. I like to use this icon. Some people just like to type. I think V does the same thing, I think. I'm not sure. Oh, hold on a second. I don't remember. I don't use it. No, is it O? Yeah, O. If you use O, it pops up your view options. So O on your keyboard or here. I like to use the icons because I'm very terrible with my keyboard. What I do strongly recommend is that have this option on, okay, length. So this way, as you're putting your member, you see the program is going to give you the length of the member that you're adding. And if it doesn't add up to 10 meters, then you know your node is not in the right place. So this gives you already an idea whether your nodes are placed properly. Then the other option that you can put on, okay, is this one here, okay, attributes. Put a check mark under end condition. End condition is what gives you the circle if you pinned, okay. Now, what you're going to do, that's going to give you, let you know if you pinned this properly. You're going to see two little circles there, okay? And how do I put a pin there? Well, I double click on this member here. And here under bending moments, what you're going to see is going to be a plus sign. Okay, so you're going to go down to where it's a pin, and you're going to pick that one, and that's how you create the pins on each end of the member. And you're just going to press OK, and that's done. And then the only place that you have to do it, you can pick them both at the same time because they're exactly the same thing. So I can pick this one and this one at the same time by holding down the control button. I right click, I go to properties, and of course I come here and I pick that, and that's going to make them both pin. So you can do them both at the same time. Okay, and you see, and that's now let me show you what happens if I change that. Okay, I'm going to change that. I'm going to change that to fixed. Okay, when I change that to fixed, like I'm going to pick this one, I'm going to leave that one on. So I'm going to change this one to fixed, properties. I'm going to change that to fixed, and you'll see what's going to happen. As soon as I make it fixed, okay, the circles are gone. That means the member is now continuous, as if I'm welding one side to the other side. Okay, it's going to be one continuous member, which is kind of defeats the purpose of having a member in here. Okay, so now I'm going to go back and properties, and of course I want it to be pinned, and that's it. Okay, so that's how you get it. So like I said, here under attributes, if you click the end conditions, you will, okay, you will see that appearing on your thing on the graphics. Okay, then once you've got the members in, once you've got the supports in, once you've got the end conditions in, well, you finish what I call part one. You finished your modeling. That's number one. Then once you finish your modeling, you're ready to move on to your loads. So what you need to do is, this is for your modeling, and then this is for your loads. So there, now you click here, okay? Now that's for your loads. So the first thing you do, you go to loads, and you go to load cases, and you go to definition, okay? And this is where you keep adding the lines, okay? P1, P2, P3, P4, P5, P6, okay? In other words, this is automatically there when you're gonna open it up, the program, okay? So therefore, you're gonna press the plus sign, you're gonna get a 2, a 3, a 4, a 5, a 6, and then you call this one SID, superimposed dead load. Then call this one snow load P1, snow load P2, snow load P3, snow load P4, okay? That's gonna be, okay? So that's how you're gonna call the load cases, okay? Now, once you've done that, well, you go back, you press OK. Well, then you double click on the member. Okay. I'm sorry, like, okay, so you're going to pick, let's say we always start with the superimposed dead load, save the project, okay. Okay, so here, now I've already done it. So you're going to double click on the member, and this is what's going to pop up. So what you're going to have is you're going to have concentrated loads, right? And you're going to have concentrated loads starting at 0 at the beginning of the member, and then at every 2 meters, you're going to have a concentrated load. And then, of course, the negative sign means it goes downwards, right? And the positive sign goes upwards. So you're going to have to put a negative sign here. And then you put the numerical value. And this is important, okay? We'll talk about this when we do the trusses, but this is the orientation of the load. Put it at 90 degrees, put it global. Perfect. You don't have to change anything here. Everything's good. When we do the trusses, I'll explain the difference, okay? But for here, it's a horizontal member. Leave it the way it is. So you do that for the first member. Then you double click on the second member. And of course, go to concentrate. I only have one load on that member because it's only 2.5 meters long and it's at 18 meters. Then I click on the third member, and of course I go to concentrated, and I'll have 2 loads on that member, except one starts at 1.5 meters away because this is already 0.5 meter away, and the other one's at 3.5. So I'm placing it properly, and so on. So, and then I do it all the way across. And then if you want, you can copy, like you can copy and paste this information. So, or you can just go ahead and redo it. Like, in other words, then you go to snow load number 1, okay? And you do the same thing. In other words, you click on this and you start. Concentrate a load, and of course the same dimensions here, 2, 4, 6, 8. This one's not necessary. Oh, why is that at 0? Anyway, something's wrong. For some reason, I must have clicked that after. Anyways. Okay, so, and there you go. And then of course you have to do, for each member, you have to load them for P1, and then load them for P2, and load them for P3. And if I'm not mistaken, I don't want to do it here because I don't have it. I don't want to modify my file, but all loads. Let's see. That's all loads put together, which is pretty useless. Okay, and then once you finished all your loading for all like your superimposed dead load, your P1, your P2, your P3, and your P4, okay, then you're ready to tell the program how to combine these loads, and then you're going to go to load combination, and you put definitions, and of course this is okay. Call it ultimate limit states. Okay, USD ultimate ULS. I call it limit states design. I made a mistake. Doesn't matter. But this is for my strength. This is I should have renamed this, but don't do what the mistake. That makes no difference at this point. And this is for my serviceability. Okay. So I have 1, 2, 3, 4, 5. So these are all the loads that I have, right? That I have, you know, that's you're going to see that pop up when you, then this is the load factor. So I click on the first one, and this is where I press the plus sign, and I put 1.25 the dead load, 1.25 the superimposed live load, and 1.5 the snow load. And then I go to number, like I'll do all the LSDs at the same time. Okay, then I do the same thing here. I double click on here and I put plus, plus, plus. I mean, this is already going to, the dead load's already going to show up here. It's going to be a factor of 1.0. You change it to 1.25. Then you're going to have to come here and call up your superimposed dead load, and then it's going to pop up, and then you're going to be putting the load factor. Then you come here and you're going to call up your snow load number 2, and it's going to come up and you put it in there. So like, for example, so that's how, if you don't remember, that's how that gets done. So this is how you do all your load combinations. Once all of that is done, that means all your combinations are done. Then if you want, okay, and you should, I'll show you how to do that now. If you want, once all your combinations are done, you're going to go ahead and look at your envelope. So you go to your load envelopes. So here it is. Okay, so in other words, you're going to press so I'm going to have, I have 2 envelopes. I have one for, this is the strength, and one for serviceability. So this is where I add them here. Then once I add them here, I come here and I simply say for strength, well, these are all the loads I want you to combine for strength. In other words, P1, P2, P3, P4. Okay. And then for serviceability, I want you to add S1, S2, S3, S4. Now, people are going to say, like, where's your dead load? Because don't forget, when you assign P1, you've already assigned a dead load to this one. Okay, this is not just a snow load. Okay, and then for serviceability, you've only assigned a snow load here. So that's how you were able to differentiate, and that's how you create your envelopes. And now, if you want to see what this thing's going to look like, after you run your analysis, okay. Say yes, analyze. For some reason, of course, it had to, and I have no idea why it's not, like, it should run the analysis in about 30 seconds, and then all of a sudden I'm not running the analysis.
It
So
says that the material and the member shapes are missing.
Well, I should get an error message, right? Shouldn't I be getting an error message? I have no idea why the program's not responding. I have no idea why the program's not responding. But anyways, like, it should definitely run the analysis at this point, because I don't know what changes I made that, let me just save. Okay. Weird.
Sir, don't
Yeah.
say. Did you already save it? Because you cannot save it and then reopen the file and then check.
Well, I can do whatever change I want, save it, and rerun my analysis if I make a modification. That's for sure. Understand? But hold on a second. I want to try something else because I don't know. I want to see if it happens again. Hold on a second.
Maybe you have to click on activate load cases. I'm not sure.
No, I mean like I just want to see what the where the glitch is. You understand? Okay, deal. Well, for some reason, oh, there you go. I don't know what happened. There you go. That's how fast it is, you understand? So here you go. Now, if you want to see a load case, okay, you just pick one here. For example, load case number 1, and there's your moment diagram, okay? And then if you want to see the envelope, here's the envelopes. I don't know what happened. Anyways, look, guys, sometimes these things, and that's the envelope. So in other words, what the program did is that it went to get the highest bending moment for one case and the lowest, the maximum minimum. And so here's the envelope for the bending moments. And then, of course, if you want to see the shears, you simply come here. I'm sorry, results. You take off the bending moments and you look at the shears, and you're going to give you the shear envelope. So there's a shear envelope for all the members. And then if you want to see the, you understand, if you want to see the reactions, in other words, for your columns and so on, we'll talk about this. So if you want to see reactions, so you take this off and you go look at your reactions. Of course, you don't have any RXs because it's all pinned and everything else, RY. So here's the reaction. So you're going to use, we're going to come back to this. Okay, so this is it. And this is the, and that's what you're going to end up seeing. Okay, so that's basically it, guys. So let me just stop the.
Sir.
Yeah.
Just for the position of the concentrated load, I'm just kind of confused when it comes to like, how do you know? Like, do we start at position 0, then we add?
Well,
twice and then it's
okay.
1?
Hold on a second. Let me stop sharing. Okay, and let me. Okay, so Omar. Okay, yeah. I'll because I'd rather do this on the whiteboard. It'd be easier to follow. Okay, fair enough.
Okay.
Wow, let me clear. Okay, so basically, look, Omar. What you have to keep in mind is this is your member, right? Fair enough, and it has a length. So let's start with the very first one, right?
Yeah.
Now, as far as ADA goes, in terms of distance, where does the member begin?
From 0.
So therefore, that's 0. And where does the member end?
At the specified length.
Which is
10.
like, let's look at our case, which is 10 meters. Okay, you understand?
Yeah.
So therefore, when you put in the first load down, the first load should be right here, because that's okay. And therefore, what's the distance?
0.
Exactly. So the first load will go at 0. Then what would be the second distance?
2.
2 meters.
No, I mean the first one is easy, but when you go to 2.5, then if you put at 0.
No, at 2.5, you don't put one at 0.
That's my question. And the one after, like, it just.
Well, that's what I'm saying. I gave you all that information on the PowerPoint because this is the one that's 2.5 now, right?
Yeah.
Okay, so this member is 2.5. Now, don't forget, on this member here, you've already put the load here, so you don't duplicate that load. That load's already there. So you don't put another one here, then you're going to have twice that load here. Then you move over by 2.5 on this member, okay? So here you don't put nothing at 0 because I put it on this member here, so I don't have to put on this member here. And therefore, this one's at 2.5, and that's it for that member. So for this is member number 1, this is member number 2.
Okay, if there's like they're close together, like they're like 0.5 millimeters. I mean meters apart. Is that good or not?
What do you mean by 0? They're 2
Like,
meters.
I mean,
They're 2 meters apart. The open web steel joists are at every 2 meters. So I have one at 2, one at 4, one at 6.
True, but let's say after 2.5, if you start at
then here this is where the member ends. That's got nothing to do with where the load is positioned. After that, I have another member in here. Okay, so now
I can start from 0 here.
No. Where does the joist sit on that member? How far is it from here to the end of this member?
0.5.
0.5. How far is this load from this load?
Should be 2.
2. So where does this load start with respect to the member?
1.5.
Exactly. So this for that third member, the first load is at 1.5. And where's the second load going to be applied? So for that member, the first load gets applied at 1.5, and then the second load gets applied at 3.5 because it's 2 meters away from there. In other words, that's what I was telling you. When you add your members, make sure you go from here to here, because even when you apply the loads, the program is going to look at how you put your I and your J node, I and J. So on the third member, this is member number 3. The first load is at 1.5, and the second load is at 3.5. And you're done for this member. Then you got to go to the next one, right? So this member goes all the way to here, and then you have to decide where this one starts on this member. So.
Okay, then we have to calculate it. Okay.
You understand? And then like what you have to look at is like, where does this one end? And if you want, I can show you where that is. Let me just go back to, I have to open up ADA, but did I show you that? No, I didn't show you that. But that's all. Okay, hold on a second. Let me just clear the drawing here. Let me stop sharing this. Let me share the ADA with you.
I have a question.
Yes. Let me just finish with the loads with Omar, and then I'll come to your question. Okay. So Omar, here. I don't care. As far as the distance goes, they're all the same. I don't care. The values are different, but whether it's superimposed dead load, P1, P2, they're all in the same positions. Okay.
Can you hold them all like as a one piece and then do it all from the beginning, like instead of doing piece by piece?
Well, you have to load each member. You have no choice. Each member has to have a load. Each load case, if it happens to fall on that member, you have to add it to that member. Yes. Why? I don't understand what you mean by.
I mean, what I'm doing right now, I'm like picking line by line, like
no. I don't understand what you mean line by line.
I mean member by member, and then
okay.
Go there
yeah. See, so this is member. Okay. So in other words, here are my concentrated loads for that member. Okay.
Yeah, exactly.
These are the distances, and these are the values of the force.
That's this is the only way, or we can do it like we can.
That's the only way. That's the only way the program you'll be able to put your load cases on your members. I mean, why?
Okay. I'm just making sure because I thought I can just like select all of them and then start from 0 till.
No, you can't because you can't select them all because if you select them all, it's going to put on every one. It's going to put the information you put into the spreadsheet. And like in other words, this member here does not have the same, like none of them are the same. Like the only time you can do that if they're all the same, right? So is this member here the same as this member here? No, it's the mirror image. So what are you going to do there? Okay. Is this member here, I'm sorry, is this member here the same as this one here? No, you understand? So you have to pick each member and load each member individually.
Okay, now it's clear. Thank
You
you.
understand? The only thing you can do, you can try this, okay, is that you can do this, okay? You can try to copy that, okay? Copy, okay? Then when you come to snow load number 2, instead of putting the distances, you can paste the distances for snow load number 2 and then just change these values here. But at least you'll have the distances in your spreadsheet.
Okay, makes sense. Okay.
That's the only thing you can do if you want to make it a little bit faster. You understand? So in other words, but if you have this, like Omar, I don't know, I should have stressed this at the beginning. Like, before I go to ADA, you understand? I do this all on paper. In other words, I say, well, this load here is at 0. This one here is at 2 point, at whatever it is. You understand? Look, okay. So in other words, when I come to this member here, see? The concentrate load. The first one's applied at 1.5, the next one's applied at 3.5 for this member here. But I already had that worked out on my piece of paper. You understand? And then I can put the information in the program. Everybody rushes to the program without doing the basic information required to put into the program. And that's what I find that happens with ADA, that happens with everything. Everybody's so anxious to get started that they don't realize that they have a lot of, let's call it, homework to do before they can actually go to the computer and start feeding the information. Otherwise, you're going to be guessing and you won't even know what you're doing. So for example, even here, for example, the length of these members, I had to work out before I was able to, I had to work out where this node was. I had to work out where that node was on a piece of paper so that when I went to put in my node and the information, I already had that information on a piece of paper. So even if it's a software, there is, calculations you have to do before so that you know what to input into the program. Now, for example, this is okay. And then look for the next member. Okay. Here I only have one load and it's at 0.2 from the end of the member. And that's why it's, you see, and that's where this load is on this member. And then for this one here, well, this one is right across the whole member. So I go, and so on. But I know that if I put this load here at the very end here, I don't put it on this member because it's already on this member. Okay. And then this one here, same thing. Okay. This one happens to be at 2 meters away from the reaction area. And that's why each position is different. So Omar, you cannot pick all the members and put them in at once. No.
Okay.
No, I'm just repeating, telling you what you should be doing and why you can't do it, because the program is structured a certain way and the input has to be, based on how the spreadsheets can actually take your data and then take those and send it to the, let's call it, to the algorithm that the program has to be able to run the analysis. Okay. So
that's exactly why I asked you the question. If I would have thought it would have worked, I wouldn't ask you.
No, I know. I'm letting you know. I'm trying to make you understand why you can't do it that way, because each member has a specific location. Okay. And that's what you have to be careful about ADA, is that if all of a sudden I happen to pick 2 members and I start loading them, unless they are exactly the same, the magnitude of the load and the location of the load, it would be incorrect. Okay.
Thank you.
No problem. So does somebody else have a question?
Sir.
It was answered already.
Sorry?
It was answered already, how to copy and paste the data.
How to copy and paste?
Yeah.
Well, okay. I'm gonna start a new file because I don't want to screw up my file. Hold on a second. Okay. So I'm just gonna very quickly create a new structure, and because like I said, I don't want to play with my file because I've already done it all, and then all of a sudden I might do something and I might not have, I have to go back and try to see what I modified. Structure nodes. Okay. Okay. Okay, hold on. I'm not going to spend much time on this, but that's what I mean. That's what happens when you don't get rid of those pop-ups. Okay, I'm just going to okay, so let's say I load this member here. Okay, for some reason I'm going to have to go to load cases. Load cases definition. I'm going to create dead load. I'm going to call SID, and then this one I'll call it the snow P1. Okay, and then of course this is, I'm going to define what these loads are according to the, this one's a dead load. Okay. This one is a snow load. I mean, you don't have to do this, but it's good to put it in case the program has something built into it that's going to prevent you from making a mistake. There's a snow load, and so on. I'll just do it for 2 members. Hold on a second. I just want to see what the length of this member is. Okay, so let me just, hold on. I'm going to go change something here so that we can make it. Okay, this one's 10. 12.5. And 20. Okay, I just want to, okay, so I'm going to now, I'm going to go to my loads. I'm going to do a superimpose dead load, save project. No, I don't want to save it. Okay, so now I'm going to double click on the member. Oh, I got to pick superimpose dead load. No, yes, okay. It's going to ask me, okay. Okay, anyway, so I'm going to double click on the member. And I'm going to go to concentrate load, and I'm going to put five here. 1, 2, 3, 4, 5. First one's at 0. Next one's at 2. Next one's at 4. Next one's at 6. Next one's at 8. And the last one's at 10. Okay. And here I'm going to put minus 18. It doesn't matter. I should have put minus 9, but minus 9. And then minus 18. Oh, yeah, there's a way of. Okay, hold on. I only put 2 in. God damn it. 4. 6. 8. 10. Okay, so this minus 18. Trying to remember, I think there's even a way to minus 18, doesn't matter. Minus 18, I think there's a way to the program, you can put them all in at the same time, minus 18. Okay, so, okay. So there, now I've got this member loaded, right? So what I can do is I can go back to this member here. If I'm not mistaken, I can at least copy this information here, or copy this information here, whatever I want to copy. copy. Okay. And then when I come to do the snow load pattern 1, I double click on the member and oh no, here we go. There you go. You just do paste. At least you'll have all the space, and then all you got to do is change the value.
Okay.
You understand, Maxime? It's just
Yeah.
Maxime. It's the same. Are you familiar with Excel?
Yeah.
These are Excel spreadsheets. That's all they are. Okay. So whatever you can do in Excel, you can probably do to these spreadsheets, and then a little bit more. I'm trying to remember. Yeah, you can do, like, for example, once you do this, look, Maxime, like, see here, I can take all of this, click here, and say replace, okay, and what's the new value? I think it was 45.
Yeah.
Okay, and there you go. It's all 45. You can do it all in one shot. You understand?
Okay.
So, and then this, you know what I mean? Like this one, you can just change it. But if there's repetitive ones, you click on it, you right click, you say replace, and then you put in a new value. And this way, at least, if you know that your distances are correct for your superimposed dead load, then you won't screw up for all the other ones by copying and then modifying the, you understand? That's to me, I think that's the fastest way you can do it, you understand? So once I paste this, I simply highlight the things, I right click, I say replace, okay? So fair enough.
Yeah.
Then here I can either put modify, or I can simply rewrite the value. You understand? Whatever is the easiest for you to do. Do you follow what I'm saying?
Mm-hmm.
And then that's it. Oh, you see, I forgot to put the negative sign. See? But yeah, okay, but you appreciate what I'm doing, right?
Yeah, I see.
Okay, so that's what I mean. Like, you can copy and paste. Like, you can take your once you got your superimposed dead loads and you have all the right distances. Okay, once you have that, I'm going to close this. Okay. So once you have that and you see that it's all nicely, you know, sound like this is another thing, but visually you see that they're all nicely, you know, spaced on in theory, that means you've done it correctly, right? And if you see that all the values are correct, well, then once you know that all your spacing on each member is correct, then once you go to the other load cases, just copy and paste and then replace the value. Copy and paste, replace the value. Okay.
Okay, because I thought you can copy and paste like the whole old case over and over again.
I don't know if I would. I don't know if I never did that. You're probably right. You can try it. If you do figure it out, let me know. I'd appreciate it.
I tried it, but it's not possible.
Okay, so see, that's why I've never done it before, because I never thought it was possible, and you're telling me that it's not possible, because I don't think it's possible. See, if you understand the logic of the program, you understand? The logic of the program is that what it does is that it has little spreadsheets for every individual member of your structure. You know, for example, okay, like this here, okay, let me just, I want you to understand what you see. Okay, first of all, I have to get out of here. I have to go to structures, okay? So when I come here and I do nodes, this is a spreadsheet, Maxime.
Yeah.
Understand? And therefore, what you're doing is that you're putting the information or the values that the program is going to come and take in order to create the, you know, to create the structure, or to, I should say, to model the structure, okay? And then it will take these values to then do the other calculations that the program has, in other words, all the other algorithms that the program has, okay? And then, so that's why the program, the way that this program is structured is that each spreadsheet is the data that the program has been, that's how the program has been, and each spreadsheet is where the program goes and takes the information, okay? So in other words, every one of these things, okay, every one of these things are spreadsheets. And then it goes stored into this file, this particular file, which, okay. And then after that, you're going to, and that's why I don't think you can, you know, it's just like same thing in Excel. For example, if I have one spreadsheet in Excel that's for one particular thing, I don't think I can take, and then I have something on another sheet and I have something on another sheet. I don't think I could take all three sheets and put them into one spreadsheet. Do you follow what I'm saying? I think each spreadsheet has to be modified. I can probably copy from one spreadsheet into another spreadsheet, but I don't think I can take 1, 2, 3, and then put all of that on another spreadsheet, and hopefully it's going to give me the, you know,
It won't work. It won't work.
it won't work, you see. So I mean, the program is great, but you know, it's not, it's because here you're starting to appreciate that, but at least once you've done one load case, you can, you know, paste and replace. So at least you don't have to enter all the other values, you understand? Which makes it a little bit faster. And at the same time, if the first one's done correctly, you'll minimize making mistakes for all the other members.
I kind of now guessed why you can copy and paste like the whole load case, because each member has its...
Call up a company called Graytech and ask and talk to the programmer.
No, because like by seeing how the program works, like each member has its own spreadsheet with every information.
Yeah.
And they're like independent.
Yeah. Yeah. So gentlemen, I don't know if you realize it, but we went way over our limit. Stop sharing. Put this on pause.